we have been working on the CO2 capture and utilization, and today I want to share some of our recent findings on this one. People are trying to utilize CO2. We know the problems associated with CO2, but the amount of CO2 produced with the use of different energy sources, either it is the crude oil, that is liquid, coal and natural gas, which we use for all our energy purposes and transport sections. And the utilization is increasing, and at the same time, the CO2 accumulation is also going on. And Professor Reddy showed the amount of CO2 in ppms. And of course, people started using the renewable in place of the conventional fossil fuels, but still, because of the rapid development, still we are dependent on these natural resources, and that will be continue another 30 to 40 years. But keeping that, the committed reduction in the CO2, India have the target to go to net zero by 2047. We have been started working on CO2 conversion, and as you know, the CO2, its greenhouse effect. Apart from the CO2, methane is the another one from the particularly where in the coal bed methane. These two greenhouse gases can be used to convert them into useful chemicals. So that in that direction we started working. So when we look into the CO2 emissions by different countries, India is still less emitting the CO2 in terms of its total population and the GDP compared to other the Western countries. But we started working on the conversion of CO2 into useful compounds. But the amount of CO2 generating from the refineries, which is in the pure form, people are trying using to convert into small chemicals like carbonates, glycerol carbonate, what Professor Venkat mentioned. But to really mitigate the CO2, you have to look for the generation of the energy related resources. Like one, that is the people started working on methanol and DME. From methanol you can make DME, and DME will go into as a substitute for diesel. Then the maximum CO2 can be utilized when we look into these directions. In that direction, one is the reforming reaction, where this methane and CO2 can be converted into syngas. Syngas is as we know, is the main raw material for the synthesis of methanol. And from the syngas, you can make a variety of chemicals. So in this direction, present the practice is syngas is produced by the steam reforming of methane using water and oxygen, or by the partial oxidation, where you will get the syngas, and from FT synthesis methanol they produce synthetic fuel or the methanol and DME. But when you look into the CO2, when you use CO2 and methane, you can do two types of reformings. One is dry reforming and another one is bioreforming. In the dry reforming, you will end up with 1:1 mole ratio of CO and hydrogen, and that may not be the suitable for production of methanol. So, and another aspect is in the dry reforming is forms a lot of carbon because there is no oxygen content in that, and the catalyst life is a big issue there. So then people started looking into the combination of this steam methane reforming and dry reforming. Then it is called the bioreforming, where you can use water, and then you can produce 1:2 mole ratio of the syngas, and which is suitable for the production of methanol. So at the same time, you can avoid the coke formation because there is steam in the system, so it will reduce the formation of coke during. But the main problem in this is the activation of the inert CO2 molecule, and most of these reactions takes place at a high temperature. So there are the two challenges where you have to activate this CO2 molecule, and at the same time you have to have a stable catalyst. In this direction, we started our work for this bioreforming. If you look into the chemistry of this, is simple, and this reforming reaction is a highly endothermic reaction, and because to activate this methane and CO2 you require high energy, and the other possible reactions during the reaction all leads to the formation of coke. So you have to develop a catalyst which can overcome these drawbacks in this bioreforming reactions. So during this bioreforming, you can produce the syngas. I said the syngas is the highly useful raw material for synthesis of different bulk chemicals or the fine chemicals, energy and other things. But as we know, this is going into various chemicals and fuels. So for coming into the CO2 methane bioreforming, different catalytic systems are explored. One is the noble metal based and non-noble metal based. Noble metal catalysts are good, but they activate at a relatively low temperature, but they are associated with because you need a high amount of this noble metal content on the supported system, and there is other possibility is the agglomeration of this noble metal during a time, and when there is a coke formation, these catalysts are readily deactivated because the noble metals are more prone towards coke formation. And coming to the non-noble metal catalyst, mainly nickel and cobalt are used. Nickel is extensively used for the reforming reaction. The methane steam reforming, it is the active catalyst, and it is in the supported form. And the other issue with the nickel catalyst is its reducibility when you support on the mix different oxides. And the activity of the reforming reaction depends upon the amount of this metal available on the surface. And people started looking into other the structural oxides like perovskites, where you have a controlled because where you can reduce the agglomeration of these metal particles, and people started in this direction. So we are also working on the nickel based and cobalt based systems, both in the supported systems and also in the perovskite based systems. So these are the systems we selected in our study, where we used different metal oxides as supports. When we did with the single metal oxides, where the activation of CO2 is limited, because here this reaction demands the nickel sites and also the basicity of the support, because CO2 is an acidic molecule, so its absorption requires some of the basic sites. So the basic sites associated with mainly with the support. So in that sense, we used different mixed oxides which are having the basicity, and also the stability is also an important aspect. In that one, we prepared this strontium based mixed oxide systems and lanthanum based mixed oxide systems, and also this lanthanum strontium incorporated nickel zirconium perovskite systems. I will share some of our results on this system. And the support, the mixed oxides, either it is a lanthanum strontium or lanthanum based, prepared by the co-precipitation method, where we used the simple nitrate precursors, and then we used the precipitating agent based solution, and then calcined, and then we got the mixed oxide. Once the mixed oxide is formed in the different ratios, then that is used as a support to impregnate the nickel. By taking the nickel nitrate, we did the impregnation, and we prepared this catalyst. And in the perovskites, we used the citrate method to synthesize the perovskites. So these are the systems we evaluated for this, and we did the thorough characterization to understand the surface structural properties of these catalysts. And we evaluated in the continuous vapor phase at high temperature. Still, we are concerned about the temperatures, but first we try to understand the nature of the catalyst for this particular reaction, and we did in the temperature range of 650 to 700 at very high gas hour space velocities. which is this is the very important aspect, because to have the high throughput of this CO2 and methane to convert on this catalyst surface. So these are some of the results on the lanthanum strontium system, with varying the molar ratio of this lanthanum strontium. With particular this molar ratio, we got the high activity, and we also varied the nickel content from the 3% to 15%. Around 12% nickel gave the high activity with the lanthanum strontium mole ratio of 3:1. So further, this is the reaction studied in this temperature range 650 to 800 degrees. As the reaction temperature increasing, both the conversion and also both the conversion of methane and CO2 increase, because it is a highly endothermic reaction. We expected this increase, and importantly, the syngas ratio is close to 2, and then we characterized this catalyst. Because when we prepared, we observed the mixed oxide phase of the mixed oxide support, and when we do the reaction, we reduce the catalyst, because the nickel is in the metallic form, it is active. So when we reduced it, we observed the nickel metallic state. And then here the important aspect is the dispersion of the nickel. So the nickel dispersion is dependent on the support. The support which is having 3:1 has resulted in high dispersion of the nickel. That's why that particular catalyst gave high activity. And also the nickel is, I will show the next slide. Here we studied the reducibility of the nickel. So the nickel which is in the reduction form, so nickel is not reduced easily on the metal oxide. So we did the temperature program reduction, and this particular 3:1 has the high reducibility, but at high temperature. But whereas this catalyst, the reducibility is low but relative, because the highly interacted nickel particles are not easily reduced. But when we have because we did reduction at this particular temperature, so we got more amount of the nickel, and the nickel is well dispersed at this particular composition. And also we studied the basicity of the catalyst by the CO2 temperature program desorption, and you can see this is the rate where the CO2 adsorbed on the strong basic sites will come at the high temperature desorption. So this particular catalyst also having very strong basic sites. So this characterization and integrating with the observed results indicated that the nickel is well dispersed on this particular composition, and that particular composite oxide is having strong basic sites. That's why this particular catalyst gave a good activity for this bi-reforming of methane with CO2. And the important aspect in this catalyst is its stability. So we continued this reaction for a period of 500 hours. Continuously we did 24/7, and you can see we got almost stable conversion, and also with close to 2 hydrogen to CO molar ratio. That means the catalyst which is having a well dispersed nickel and the support which is having the reasonable amount of basicity is the required catalyst for the bi-reforming of CO2. And further we also continued the series strontium system, where here also the reducibility, of course this is also we did with the monoxides. The reducibility is more in the mixed oxides, and also this particular composition where we have a strong interaction between the ceria and strontium. Dr. Reddy explained about the role of ceria and its interactions, and this particular here in this case the mole ratio with 1:1. In that earlier case it is a different mole ratio, but here with the 1:1 ratio of the ceria strontium gave the better activity compared to. So that means depending upon the second metal oxide to the strontium is influencing the basicity of that particular oxide. So that means the composition is also very important in designing the catalyst for this bioreforming reactions. And this catalyst also we studied for a period of 250, and after 250 what we did, still it showed stable activity. Then we got certain doubt whether this catalyst will continue further or not. Then what we did is we characterized the spent catalyst, and we able to observe the formation of around after 250 hours a small amount of coke is observed in this particular catalyst. So that's why we stopped at this 250 hours, but still this catalyst has the reasonable stability. And coming to the lanthanum based systems, where we did in this one here the catalyst with lanthanum strontium 1:1 ratio shows the better activity, where the nickel here in this case 8% is suitable to get the high dispersion when compared with the other strontium systems, because this lanthanum seria has the tendency to disperse more compared to the strontium based system. And also here we didn't get much strong basicity as in the case of strontium. We expected, because strontium is more basic compared to this lanthanum, and cerium is also not that basic, is like amphoteric. So but here we have more amount of medium sites. Those are enough to attract the CO2 and does the reaction. And in this case, and we studied the lanthanum zirconium system also. In this one, the reducibility is also varied with the mole ratio of the lanthanum zirconia. And you can see here in the lanthanum zirconia with 3:1 molar ratio, but where in the case of lanthanum strontium it is a 1:1. And when we have a more amphoteric nature of zirconia, then we need more amount of lanthanum, because the dispersion and the basicity is mainly affecting the basic oxide, either it may be the strontium or lanthanum. When you use the amphoteric or acidic, then you require more amount of the basic metal oxide to get a reasonable amount of the basicity in the catalyst. So these different compositions we did to understand the role of the different mixed oxides in creating the basicity for this particular catalyst. So here this particular composition has the strong basicity, and still this catalyst also we studied, because for every system we cannot do 500 hours. It is very difficult to do 500 hours continuously in a research lab. But to test the stability of this catalyst, we did for 100 hours, and it showed the reasonable activity. And coming to the perovskites, where we did, we thought the movement of the nickel will be different when compared with the mixed oxides in the perovskites. So we prepared different perovskites. Here also again what we did, we took the same base oxides and varied their compositions. And here we did the lanthanum and strontium, we varied their compositions, and then we studied the strontium composition is varied from 1 to 0.1 to 0.8, and then you can see the basicity variation. And these perovskites are having very low surface area, because we calcined at 800 degrees. Of course, when we did under the reaction conditions, they are no more maybe in the perovskite structure, but there may be clusters of the mixed oxides. And then the reducibility, still we have a issue with when we have more amount of strontium, the reducibility is not so good for the nickel. And and the catalyst activity, if you see, with the low amount of the strontium and more amount of the lanthanum, perovskite gave the better activity. And we expected, with the increasing the strontium, we expected the increase in the basicity so that it may give the more. But the problem is then it retarded the reduction of the nickel. So that means you required both the basicity and also the reduced nickel particles on the well dispersed nickel. These two things are required. That's why even though you have a more basicity, that doesn't give the required activity. So that's how you have to play with the dispersion of the nickel and also the minimum requirement, minimum amount of the basicity. These are the two basic points required for the bioreforming of the CO2. So this catalyst also and further I think one of my colleague did the computation DFT studies, and he proved that the lower concentration of zirconia favors the stability, and the minimum amount of strontium both are required to have the stable system, and these results are supporting with our experimental observations. And this catalyst also studied for 100 hours. All the catalysts we studied for 100 hours, and then we analyzed the carbon composition of the spent catalyst, and this, with increasing the strontium, we observed the more amount of carbon deposition on the surface of the catalyst. So with the lower amount of the strontium, and which resulted in the less accumulation of the carbon on the support, and that means the minimum amount of the basicity is required to avoid the carbon deposition, and also with more strong amount of basicity sometimes retards the reduction of the nickel particle size. So you have to tune between these two factors and to develop the catalyst. So from these different studies on different catalytic systems, we are able to understand the basic requirements for this particular reforming reaction. So to conclude, the nickel supported base mixed oxide catalysts are active for this bioreforming reaction. So the reducibility, as I mentioned, the reducibility of the nickel and its dispersion is the key for this reaction, and it depends on the nature of the mixed oxide, and the basicity of the mixed oxide plays in the adsorption of the CO2 and activation of the CO2. So perovskite based catalysts not only delivering the high dispersion but also increasing the stability, and then the sintering is less compared to the simple nickel supported on simple oxides. So when you develop, we are working on this because it is only the initial understanding, but our target is to develop catalyst with more than 1,000 hours in the laboratory scale. Thank you for your attention.
Long live India and France friendship.